Okay, welcome back. Now I'm going to do a demo. I'm calling it block tipping over the edge of a table. This is also a good problem that you can do in physics, and then you can also simulate it. I'm going to have a block here of a certain height, and then it has a certain width. They don't necessarily have to be the same. And then the block has a certain initial velocity, and then it's going to come, and the edge of the table I'm going to put some kind of an obstruction. And then my question is going to be, what needs to be the initial velocity of what's the minimum initial velocity of the block so that when it comes and hits the obstruction, the block tips over, right? The block tips over and then completely falls off the table, right? So of course, if the block height was very short and the width was very long, it would almost never tip over. It would come and hit the corner and it would just bounce back, right? If the block was really high, right, and the width was very short, it would come pretty much, as long as it hit something, it would tip over very easily. So the way I'm going to do, you can run this experiment with a cube, or you can run it so that the height and the width are not too much different from each other. So in my case, I'm going to have a situation where the height is going to be this one, right? And then the width is going to be this one. This dimension doesn't really matter. Now let me measure the dimensions. My height is 7.4 centimeters. And then my width is going to be smaller than that. 4.6 centimeters. Okay? So 4.6 centimeters. So my velocity is not going to have to be that big because the width is smaller than the height. So it's going to come, as long as it has a certain initial velocity, it's going to tip over. So let me show you here at the edge of the table. Will be relatable to that situation. So then I'm going to zoom out a little bit so you can see here. Okay, so then all I have to do is give this a slight push. You see now, it didn't have enough velocity. So it kind of came and then it went back like that. A little bit faster, not enough. See, it tipped over. See, so if it has sufficient velocity, it's going to come and tip over. Okay. Now, if I did it the other way, it would have to have too high of a velocity. You see, it just bounces back. You see, so it doesn't work that way. So it's got to come like this and tip over. You see? So now that we have the height and the width, let's start the calculations. So we have the height like this, 7.4 centimeters, and then the width. So it's coming with a certain initial velocity. Right? So the first thing to ask ourselves is the collision of the block with the edge obstacle, is that the elastic collision or inelastic collision? Okay, and the answer is that it is actually an inelastic collision. It comes and the translational motion stops, right? And its kinetic energy is lost due to the obstruction that is there. After the collision, the initial angular momentum of the object is conserved, but not its kinetic energy, right? We're going to say the initial angular momentum of the object, L initial is L final. The initial angular momentum is mv initial minimum times the height of the center of mass. This is the center of mass, like this. The height of the center of mass from the pivot point. So this distance is what we need, right? So I'm using the equation, angular momentum is mvh, where h is defined from the center of mass of the object to the pivot point about which it's going to be turning, right? So in our case, that is equal to half the height of the object, right? h over 2, right? Then that's going to be equal to the angular momentum that it has right after the collision. So angular momentum is conserved because when it hits this thing, it starts to turn like this with a final angular velocity omega, right? So then I'm going to set this equal to I final, omega final, okay? So then I have here mv initial minimum, h over 2. What is I final? Well, we need to calculate the moment of inertia of the object about the front pivot point. So we use the equation, moment of inertia about the center of mass is 1/12 m h squared plus w squared, right? The axis is coming out of the board. The only dimensions that matter are the height and the width. The dimension of the block coming out of the board does not matter. So that's the moment of inertia about the center of mass. Then I use the parallel axis theorem. I shift it by this distance, md squared, right? So what is that distance? Well, the distance is squared is going to be, this is w over 2, this is h over 2. So it's going to be h squared over 4 plus w squared over 4. So 1/12 m L squared plus W squared plus M H squared over 4 plus M L squared over 4, right? So then we can combine this and then 1/12 ML squared. So I can put this here on the right. I can put it here, 1/12 ML squared plus 1/4 ML squared. And then same thing is going to happen, 1/12 mw squared plus 1/3 mw squared. So then that's going to be equal to what? This is, I can multiply this by 3. It's going to be 4/12, which is 1/3. 1/3 ml squared plus, and then you're going to also have the same thing here, plus 1/3 mw squared. So they're pretty symmetric. So then I can put the moment of inertia here, 1/3 m L squared plus W squared. Okay, so we're going to be using that moment of inertia again when I do the kinetic energy calculation. So let's put it here. The moment of inertia is 1/3 m L squared plus W squared. Okay, so then I'm going to multiply that by the final angular velocity that it has right after the collision, omega final. Okay, so then we can calculate omega final in terms of the V initial. The M cancels, the M cancels, so the 3 goes over there, 3 over 2 V initial min H over, right, over L squared plus W squared. Okay, that's equal to the omega final of the rotating block right after it hits the obstacle, right? So then I'm going to say, right after the collision, because it has an angular momentum, it also has a kinetic energy of rotation, right? Kinetic energy of rotation. So the kinetic energy of rotation that it has, right? The kinetic energy of rotation starts to, as the thing rises up, it converts into potential energy, right? So that by the time that the block is in this position, where this is H, this is W, its center of mass reaches here. By the time it reaches there, if the final angular velocity is a little bit over 0, then it's going to tip over, right? So final angular velocity is going to be approximately 0, but a little bit larger than 0. So that my final omega that it has right after the collision becomes the initial omega of the rotational portion of the problem. The initial omega is equal to the final omega right after it collided with the obstacle, right? So then I'm going to say the initial kinetic energy of rotation equals to the final potential energy that it has when it is standing like this with the center of mass over the pivot point, right? So then I'm going to, let's write the omega initial here. Omega initial is equal to 3V initial min H over 2 L squared plus W squared, okay? So then let's erase this. Okay, so then the initial kinetic energy of rotation is 1/2 I omega initial squared. That's equal to the final potential energy that it has, mg, and then the h, right? Well, what is the final potential energy? It's the difference of the height of the center of mass from where it used to be to where it is if it goes over here and tips over, and then the center of mass is lying right over the pivot point, right? So it's basically this distance right here. Well, it's the same thing that we called d a minute ago when we calculated the moment of inertia. We said the ICM plus md squared. So the amount of shift from here to the pivot point, when this thing tips over, that becomes d, right? And then this is going to be h over 2. This is going to be w over 2, right? So then the d is the same d. And so that's equal to mgd. Okay, well now we can put down the moment of inertia, which is going to be 1/3 m L squared plus W squared, omega initial squared, right? And then that's going to be the moment of inertia, and then the omega initial squared, and then mg, and then the d is going to be what? Square root of, so it's going to be 1/2 square root of h squared plus w squared minus the original height of the center of mass is h over 2. H over 2. So I'm taking half of the h squared, I'm taking half of this is h squared plus w squared, and that would give me the full diagonal, and then I'm just taking half of that, right? So then the mass cancels. This half cancels this half, okay? And then it also cancels this half. So basically you multiply everything by 2, you get rid of this 2, and then the m's cancel. So then you just have 1/3 L squared plus W squared. So then what I'm going to do, I'm going to take the initial omega that we got in terms of the height, then I'm going to substitute that there. I'm going to square this number, so it's going to be 9/4, and then it's going to be h squared v initial min squared over, right, L squared plus W squared squared. And then I'm going to say g times square root of h squared plus W squared minus h. Okay, so the 3 cancels the 9. Okay. So the rest of it is just pretty much take this over there, square root it, and we will get the answer to the V initial min. And now we can put in all the values and see what answer we get. V initial min squared, 4 times the gravity, 9.8. Okay, h squared plus W squared, that's going to be 7.4 squared plus 4.6 squared over 3. H is equal to 7.4 squared. So notice in terms of units, this is centimeters. I'm not changing it to meters. It's just going to be centimeters squared over centimeters squared, right? So it's just going to cancel. It's going to have no units. And then I'm left here with meter per second squared. This one is meter per second squared. This is unitless. Okay, then this one I have to change it to meters, because this is going to be meters minus meters, so I want it to be meters times meter per second squared, which is going to be meter squared per second squared, and then I'm going to square root that, I'm going to get meter per second, right? So the only one I have to change is this square root of h squared plus w squared. So I'm going to say square root of h squared, so 0.074 squared plus 0.046 squared minus 0.074. Okay? So now let's compute all of that. 0.488 meters per second. So that's not actually that fast, for 0.488 meters per second. So if we convert that to mile per hour, multiplied by a ratio of 2.25, that's going to be 1.1 mile per hour. So you notice that when I did it, as long as it was a little bit of a velocity, it tipped over, right? So 0.488 meters per second, that's going to have to be the initial velocity in order for it to tip over. Anything less than that, it won't tip over. Anything faster than that, it will tip over, right? Now, what will happen if I switch them, right? If I switch it so that the vertical is the width and then the height is the horizontal. Now it's a lot tougher to turn over, right? So then what changes here? I put W squared and I put W here, right? So just put W squared and then W, and then that tells us the required velocity that you need. It should be quite a lot higher. So I'm going to put here 4.6 squared, and then I'm going to put here 0.046 per second. Oh, so it has to go a lot faster, right? As I surmised, it has to go a lot faster if it's like this, to the point where it was actually just bouncing back, right? It was just going and hitting the obstacle and then bouncing back. So 1.39, that's going to be about 3 times faster that it has to go that way, right? So the answer is making sense. We could also compute the percent loss of kinetic energy that occurs, since this is an inelastic collision, right? the percent loss of kinetic energy that occurs if it's coming in at that velocity, right? So if its initial velocity is 0.488, what's going to be the initial kinetic energy? The initial kinetic energy is 1/2 mv initial squared. So let's just say, for the sake of argument, it's a 1 kilogram object. So it's going to be 1/2 times 1 v initial squared, so 0.488 squared. Okay? Is the initial kinetic energy, right? So then what's going to be the final potential energy? So because right after the collision, right, it has a certain kinetic energy, right? And then that kinetic energy converts into potential energy, right? So if I can show that the final potential energy is less than the initial kinetic energy before the collision, then that shows that this is an inelastic collision, right? So all I need to do is calculate the final potential energy when it's at the top, because the final kinetic energy at the top is 0. So the final potential energy is equal to the initial kinetic energy after it collides with the obstacle. After collision with obstacle. Okay? So that's going to be mgh. So then we put 1 kilogram, 9.8, and then the h was equal to what? Square root of h squared plus w squared over 2 minus h over 2. Right? So then I can put my h and w, but put it in meters right now, right? So the final potential energy is going to be 0.0643 joules. 0.0643 joules. So you can tell that kinetic energy has been lost. So what's the percent loss of kinetic energy? So kinetic energy initial minus kinetic energy final over kinetic energy initial. So 0.119 minus 0.0643 over 0.119. Okay? 46% loss of energy. So you can see here a good problem where we're using angular momentum conservation, and then after the collision, the kinetic energy that it has is conserved and changes into potential energy, and then that gives you the required velocity for the block to tip over. Okay? Thank you very much.